Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 50, x to the power of n. After that, we'll go over an actual follow-up that big tech companies ask. Anyway, let's see what we're being asked. I love me a one-liner. We have to implement this function, which again is x raised to the power of n. Let's blindly underestimate this problem, excuse it as an easy problem, and then tell the world how trivial it is when it's really not. I'm sure everything will go very smoothly. Let's just look at an example and solve it. All right, as input, we have a base x of 2 and an exponent of 5. Together, this makes up 2 to the 5. We have to write a function to output its mathematical result. Once again, this is children's play. We just have to write code in such a way that simulates multiplying 2 by itself 5 times. Or in other words, 2 times 2 times 2 times 2 times 2. Okay, the classical approach is to use recursion, which always has two parts, the recurse and then the backtrack. On the recursive path, we can decrement our n by 1 in every single stack frame. So from 2 to the 5 to 2 to the 4. From there, what's 4 minus 1? That's 3, so we get 2 to the 3. We minus 1 to get 2 to the 2. We'll pass that into the next recursive stack frame. And from there, 2 to the 1, all the way until 2 to the 0, where we hit a base case. Why is this a base case, you ask? It's because anything, no matter the base value, to the power of 0 is equal to 1. Let's return this on the backtrack. And actually, let's rewrite this as 2 to the 0 because we're fancy elitists. Anyway, on the backtrack, this was our return type. We know we want to simulate this upwards climb to eventually return our final result of 2 to the 5, or 32. Let's not get ahead of ourselves though, one stack frame at a time, which on this one, we want to produce 2 to the 1. As the how, why not multiply 2 to the 0 by a base of 2, which is the same thing as 2 to the 1, to output 2 to the 1. I hope you remember your middle school math. This gets us exactly what we needed. Our output here can also be rewritten another way as just 2, because duh. Anyway, good work. Let's return 2 to the 1 to the parent function call. Where here, we'll do the same thing. To get 2 to the 2, we'll multiply our return type here by another base of 2. Again, it's equal to 2 to the 1 to get 2 to the 2, or in other words, 2 times 2. As per our repeated logic, we'll return this 2 to the 2 upstream and multiply it by another 2 to the 1 to get exactly 2 to the 3. Great, we're getting closer to our answer. We'll now return 2 to the 3 on the previous stack frame where we had a 2 to the 4 on the way down. What do? We times 2 to the 3 by 2 to the 1 to get 2 to the 4. Which can be verbosely expressed as 2 times 2 times 2. One last time, what's 2 to the 4 times 2 to the 1? 2 to the 5, or put another way, 2 times itself 5 times. This comes out to be 32. This is our answer. This is what we return. The time complexity is big O(n), where n is the input n, as seen here. This is because we recurse for this many times, decrementing our exponent by 1 on every iteration. This naive solution is surely widely accepted by every interviewer to have ever existed and will exist for that matter because...
貴様の拳などかほどにも効かんわい。お前はもう死んでいる。何?
Alright, nothing more chaotic than fights on a YouTube thread, but their discussion was productive and correct. There is a better approach, specifically in log n time complexity. If this is confusing, just think of a binary search algorithm where we repeatedly halve the search space by 2 on every single iteration. If we discard half the search space every time, then we have log n. In regards to our power function here, that means dividing our exponent by 2, or in half every single iteration, not by a measly 1. Okay, enough context. Let's try to simulate a similar workflow to the brute force solution and use recursion to ultimately return 2 to the 10. On the first iteration, we'll divide an n of 10 by 2 to get 2 to the 5. Now, before we move on to the next recursive call, let's show off and do some fancy mathematical refactoring. 2 to the 10 can also be expressed as 2 to the 5 times 2 to the 5. And if you don't believe me, what's 2 times itself 5 times? That comes out to be 2 times 2 times 2 times 2 times 2. Same thing with this symbol. As we just saw, 2 to the 5 is 2 times itself 5 times. Great. Now, if you take the product between the two groups, you indeed get 2 times itself 10 times. Or in other words, 2 to the 10. Therefore, it seems like if we divide the exponent in half, then it can be expressed as a product between the two halves. I feel so cool. Okay, let's move on. On the next recursive call, we had passed in a 2 to the 5. Dividing its exponent by 2 gets us 2 to the 2, to which we pass in the next function call. Hold on though, let's practice our math fundamentals. We can rewrite 2 to the 5 as 2 to the 2 times 2 to the 2. Not quite. Turns out we're missing a singular 2 to the 1. Why was that? Well, we divided an odd number by 2. And moreover, we used integer division. Thus, this yielded a rounded down output of 2. To compensate, we add back a 2 to the power of 1, which now makes this formula correct. Fantastic. As we just observed, the parity of our exponents is critical in refactoring our arithmetic expressions, so we'll keep an eye out for it. On the next function call, we had 2 to the 2. If we divide its exponent by 2, we get 2 to the 1, which on that note, because our exponent was even, we can simply rewrite 2 to the 2 as 2 to the 1 times 2 to the 1. Moving on though, here's our value. We know that 2 to the 0 times 2 to the 0 won't equal 2 to the 1. And that's because the exponent was odd. 1 is an odd integer. Therefore, we'll toss in a singular 2 to the 1 to multiply by, and perfect. This formula holds true. We'll now progress our recursive call by dividing our exponent by 2 to get 2 to the 0. This is the same base case as the brute force solution, where our exponent is 0. Recall that anything to the power of 0 is 1. Therefore, we'll terminate our recursion and return 1. This 1 right here, or to be pedantic, 2 to the 0, to continue our backtracking adventure. Let's frame what information we currently have. We have a 2 to the 0, but we want to do some math to get 2 to the 1, the value that we had on the way down. But how? Thankfully for us, we already did all the heavy lifting. Our literal formula to success is right here. That if our exponent is odd, and it is, we can multiply our return type by itself, and then by a singular 2 to the 1. All this gets us 2 to the 1, which equals what we wanted. Nice. Let's return this for the parent stack of the output. And real quick, if you're curious where I pulled this 2 to the 1 from, it's literally our input base of x. Moving on, here we have a 2 to the 1, but we want an output of 2 to the 2. As the how, we'll follow our equation. That 2 multiplied by itself is the answer. Great. There's no funny business here with even exponents like there was with odd exponents. This is our return for the upstream frame, where we'll once again mime our formula. To be exact, in code, we have an if statement to check for an odd exponent. In this case, we do have one, so we'll multiply 2 to the 2 by itself, and then by a 2 to the 1. As always, we return this to the previous function call, where we'll take 2 to the 5, our return type, double it, to arrive at 2 to the 10, or in other words, 1024. This is our answer. This is what we return. The time complexity is log n, because as we observed, we halved our exponent each time we processed it, from the 10 to the 5 to 2, 1, and then 0. The space complexity is also log n, because the number of times we iterated is the number of stack frames that we'll have in memory. Now, before we get to the code, get prepared for a rabbit hole. I'm not sure if you read the whole description of each LeetCode problem. I don't. But there does exist an edge case. What if our exponent was negative? Let's take a look. Here at Minmer headquarters, we're all about refactoring mathematical expressions to ones that we can actually comprehend. To start, we have our base of x to the power of negative n. This will equal our result, r for short. To kick things off, we don't like negatives. It introduces too many cognitive complexities, kind of like when you have triple negatives in a sentence. It's confusing, so let's do everything in our power, no pun intended, to get rid of this negative. The first thing we'll do is multiply both sides by x to the n. This gets us x to the negative n times x to the n equal result times x to the n. Now, do you remember the product rule of exponents? We've technically done it 20 or so times already, but never formally talked about it. If we're multiplying two exponents whose bases are the same, both of which are a generalized x in this case, then we'll add both exponents. Thus, this can be rewritten as x to the negative n plus n equal to r times x to the n. Turns out we can simplify this even further. What's negative n plus positive n? It's 0. This means we're left with x to the 0 equal to the unchanged r times x to the n. Now, what is anything no matter the base to the power of 0? It's 1. The last thing we'll do is isolate our result variable in this equation. That way, it'll be easier to reason with. Therefore, to get it by itself, let's divide both sides by x to the n. X to the n divided by x to the n is just 1, so they cancel each other out. We're ultimately left with 1 over x to the n equal to our output. Awesome. All this to say, if we had something like 5 to the negative 3, then we can rewrite this as 1 over 5 to the positive 3. No negative sign in sight. Great. In code, we'll do exactly that. We'll transform x of 5 to 1 over 5 and make our negative exponent positive with the absolute function to get positive n. Amazing. And speaking of code, let's write this up. First things first, while the edge case is fresh in our minds, let's quickly handle it. If we have a negative exponent, we know that if the input n is below 0, we'll return 1 over our base of x to the power of positive n, our exponent. Okay, let's get to the recursive logic. What was our one and only base case? If we ever have an exponent of 0, then we return 1. Once again, anything to the power of 0 is indeed 1. Otherwise, we'll recurse forward by calling our function and each time dividing our n by 2, essentially halving it. Please note the use of integer division. From this, we get back a mathematical output. I didn't name it in our workflow, but let's name it something like result. Now on the backtrack, if we know our exponent of n is odd, we'll return to the upstream stack frame the input base of x times result times result. If our exponent was even, then there's no singular base to multiply with. We just return result times itself. And that's it. Nice job. I hate myself for saying this, but there is an even better approach. Let's take a peek. Turns out there's a solution that doesn't use any space complexity at all. That's right, you can achieve a log n time complexity without any recursion and thus any backtrack. We'll still divide our exponent in half to retain our log n time complexity characteristics. This signifies we can have the same path going down. But if we can't backtrack up and apply math on the way back up, then we have some mysteries to unravel. Before we do though, let's take a short break and review some more math fundamentals as it pertains to exponents. To challenge ourselves, we can look at this equation in regards to this rule from another perspective. In retrospect, 2 to the 10 here was calculated in base 10, or in other words, using the decimal system where digits range from 0 to 9. But what if we looked at this in base 2, or the binary system where digits are either 0 or 1? Decimal 10 in binary is 1010, and this is base 2. I'm going to claim that this value is also equal to 2 to the 2 times 2 to the 8, just like this equation. As the how, let's closely examine this mishmash of zeros and ones. Let's have a gentle introduction. Let's just imagine that this was still a decimal number. It's read as 1010. From the right, we have the ones place, or in other words, 10 to the 0. If we move to the left by one digit, we increase by a power of 10 to get 10 to the 1. As we know, this is known as the tens place. If we move to the left by another digit, we increase by a power of 10 to get 10 to the 2. This is the hundreds place. One more time to get the thousands place, otherwise represented as 10 to the 3. As a trivial observation, because we had a non-zero here at the thousands place and here at the tens place, we can add their respective values to get 1010, the exact decimal number that we had. Okay, great. Let's do the same thing, but with binary. From the rightmost digit, working our way to the left, we don't have 10 to the 0, but we have 2 to the 0. This is literally base 2, remember? Not base 10. The value comes out to be 1. If we move to the left by 1 bit, we increase by a power of 2. So this comes out to be 2 to the 1, or 2. Following our pattern, moving one digit to the left doubles our value to 4, or in other words, 2 to the 2. One more time, we double our value from 4 to 8. 8 can be expressed as 2 to the 3. Now for the magical moment, because these two bits were set to 1, that means we add their respective values, the 8 and 2. This gets us 10. This can only mean one thing, that 2 to the 1010 is equal to 2 to decimal 10. Can you see how these two equations are equal? To be redundant, let me phrase this another way. This expression signifies that it's made up of 2 to the value of this bit, which, as we saw, is a value of 8. Therefore, 2 to the 8 is included in our resulting value. Not only that though, this expression is also made up of 2 to the value of this bit, which we also saw was 2. Therefore, 2 to the 2 is also included in our result. Very cool. Oh, and for quick funsies, leading zeros are not significant in this case. So if we added another 0 here, sure, it's the 10,000s place, but it contributes no value to our overall number since its bit was flipped to 0. With that context out of the way, let's actually dive into the problem solving of the optimal solution. Alright, we have a similar example, like the past two examples, how thrilling. To refresh, we've built enough intuition at this point to know that we should halve our exponent of n here by 2, all the way until a base case is hit. But the difference here is, since we want a space complexity of big O1, constant space, we cannot use backtracking. Okay, I'm yapping again. Let's just start halving our exponent and go from there. We have 2 to the 10. As usual, we'll half its exponent to output 2 to the 5. And here, we'll keep shrinking the exponent by half all the way until we get to 2 to the 0. As always, this is our termination case where we stop iterating. I'm aware that this is not recursion in action, but will simulate something extremely similar with an iterative approach. We'll run a while loop so long as our n exponent is not equal to 0. The moment it is, like it is here, then we break out of our loop. This shouldn't be a big jump from our previous solutions. Once again, the issue is there is no backtracking to reapply mathematics to get to our desired 2 to the 10. What do? Well, if we can't apply math on the way up in a recursive approach, why not simulate it on the way down, simultaneous with our while loop? To see how, recall this depiction. Here it is. I'll start off with this. If we're dividing an exponent of 10 by 2 on every single iteration, then we get 10, 5, 2, 1, and then 0. These exponent values do correlate with these bits. As the how, recall that 01010 literally equals 10. Also, anytime you move over by 1 bit, the value changes by a power of 2. If this is the case, then if we try to divide 10 by 2 on every single bit, then we'd surely get to 0, a base case. Alright, what a cool pattern. On these corresponding iterations, the binary values were 2 to the 0, or 1, 2 to the 1, or just 2, 4, 8, and then lastly 16, so forth and so forth. This is because binary is base 2. It doubles on each bit that you move to the left. Finally, let's make this observation. Please notice on an iteration of an odd exponent, we have a bit flipped to 1, meaning we should include a base of 2 to the power of 2 in our result. On the bit right next to it, we have a 0, which means it's false. After that though, we do have a bit of 1, which means we should include a base of 2 with an exponent of 8 also in our answer. And yes, the exponent there was indeed odd. Anyway, multiplying these two values gets us our exact desired value of 2 to the 10. That would be our answer and what we return. Okay, we're really onto something here. We can replicate this logic in our while loop. That on any iteration that we divide our exponent, we'll keep doubling the base of 2 in this case, side by side. So on the first iteration here, we'd have 2 to the 1. Then on the second iteration, where we have an exponent of 5, we'd have a doubled value of 2 to the 2. After that, when we have an exponent of 2, we'll have a double value of 2 to the 4, so on and so on. And on any given iteration that we have an odd exponent, we'll include the doubled value of 2 to the 8 in this case in our result. With this knowledge, let's go through our example in whole, where before anything, we'll initialize a variable of our base of x to 2 to the 1. In code, you'll see that I named it doubling value. On the first iteration, our exponent is 10, and it's not 0, so we'll keep going in our while loop. After that, we'll have a similar if statement to the solution before to see if our exponent is odd. It's not, it's even, so we won't include a doubling value of 2 into our answer. As a sanity check, it's true, we have a bit of 0. We'll now do two things to progress towards our base case. Yes, we'll halve n by 2 to get 5, but we'll also double our value from 2 to 4, or in other words, 2 to the 2. On the next iteration, we now have 2 to the 5. We note that our exponent is odd, which can only mean one thing. We'll include our double value of 2 to the 2 into our result, as seen here. Verifying it, we had a bit of 1, which signifies a boolean of true. As always, we'll halve our n to 2 to the 2, as well as multiply 2 to the 2 by itself to get 2 to the 4. Moving on, we have an exponent of 2, it's even, so we forgo including 2 to the 4 in our result. We end the iteration by halving n to get 2 to the 1, and at the same time, double 2 to the 4 to get 2 to the 8. Continuing on, this is what we have. 1 is indeed an odd number, so we'll include 2 to the 8 in our result. I'm a broken record at this point. 1 divided by 2 is 0, yielding 2 to the 0, and 2 to the 8 doubled is 2 to the 16. On this last iteration, we break out of our while loop because we finally have an exponent of 0. And ultimately, we have 2 to the 2 times 2 to the 8, and what do you know? The output is 2 to the 10. This is our answer. This is what we return. Our time complexity is log n, and our space complexity has been reduced to constant space. What an adventure. Let's implement this. I hope you have a good memory. We still have to cover an edge case in which we're given negative exponents. Like before, we'll transform x to 1 over x, and then we'll turn our exponent of n positive. Let's initialize everything we'll need for our while loop. That involves a result, and of course, let's return it before I forget. We'll also need a variable called doubling value that starts off as our base of x. Let's start our while loop and keep going so long as our n is not equal to 0. On each iteration, we'll do two things to progress towards our base case. As the name suggests, we'll double the value of doubling value and also cut n in half. But hold on, if our exponent was ever odd, we'll include the doubled value as a part of our result. Okay, wow, so much explanation for so little code. It really makes you think how insane some of these questions are. On that note though, I wish you luck on your interviews. Thanks for your support, and if you learned something today, please make sure you like, comment, and subscribe. Thanks.